Hello everyone, welcome back to another processing video. So this time I will be showing off my genetic algorithms project, which uses a genetic algorithm to basically calculate the best curve based on evolution, the best curve that represents the ratio of median income to median house value in California. And this is taken from an online dataset. You can see my previous videos to get more information about this. And basically, I'll just be showing you the program and then some parts of the code. I won't go over the whole thing because it is pretty complicated. There's a lot of it. Let's see. Yeah, there's quite a bit here. Just some of the key parts are necessary for the understanding of the whole process. Also, you might want to check out some other people's videos that explain machine learning, because this is very tied to that. So let's first run the program and see what it does. Alright, so allow me to explain some of the things going on the screen here. So this black line is the curve that represents the best curve of each generation, and then the generation count goes up every time that it's done checking and calculating all of the different things that must be done. Each generation is consistent of however many curves you want there to be in a generation. I have decided that 500 is a good number, and all of these numbers I will explain right now. And also we can see that the training has ended at the 302nd generation. Alright, so let's start up here in the top left. Best train RMSE is 84.79. So what does that mean? Well, that basically means that the fitness value, so to say, of this curve on the training set, which are the red dots, is a value of 84.79. So that means basically if you add up all the little differences between the red dot and the y value where the curve is at that particular x value of the dot for all of these dots, then you'll get this number with some added functions. You can look up what RMSE means on Google and you'll find some results that explain it. But basically it's a way to calculate how close a line is to an actual set of points. So like ideally it would be 0, and in the worst case it would be infinite. However, infinity is like not very possible, but basically the bigger the value, the worse the curve is. The smaller the value, the better it is, or the more representative it is of the data set. So we have these two different sets here, training and testing. So training is red, testing is green, and the third one, we'll get to it later, is the validation set, which is blue. So today I actually looked it up on Google, and it turns out that when you do machine learning, the thing you use to determine when you're supposed to stop is called the validation set, and then the thing you use to determine how good your model is called the testing set. And I actually mixed up the two. So when you see testing, that basically means validation. And I got confused about this because in a lot of the projects I've done, I have not used a validation set for the purpose of early stopping. So that was kind of confusing. However, I did figure it out now, which is better than later, so I don't feel too bad about it. So basically, the best test RMSE here, this is how well it fits to the green dots. And it's kind of to confirm that we're not trying to approximate the red too much. We're trying to fit the whole thing. So this basically tells you if you're overfitting or underfitting. And if you're overfitting, then the green line will eventually start to go up. And now let me start to explain what this kind of graph is. Basically, this is the fitness of the curve, of the best curve of each generation on the red set and the green set respectively. So you can see that the fitness gradually gets better, and lower means better in this context. So it gets closer and closer, as it also does for the green set. Let's see. And then we have the difference values here, which are basically what I use to calculate is the current fitness getting worse. So like, is the previous fitness from 100 generations ago, is that better than the current one? And if the answer is yes, and then it passes a certain threshold, then we'll stop the whole thing. So like, for example, if the okay, so in the program actually, if the testing RMSE or the validation, if it doesn't improve, which means like, you know, it decreases, the actual fitness decreases, then that means we're gonna stop right there compared to 100 generations ago. But I do make it a bit loose. Like, let's see. Yeah, here in check stop. You can also call it early stopping. That would be more more cohesive with Python's Keras library. Also, it's just known as early stopping throughout machine learning. So let's see. If the test RMSE difference is greater than 0.01, we will stop the whole thing with this write function. It writes the curve to a text file. Right here, we save the strings to this polynomial.txt text file. So it's very clear how if you don't get better, you basically just go ahead and stop the whole thing. So, oh wait, this might have been blocking the actual screen. Okay, if it was, apologies. But the code isn't really necessary to understand. If the green curve goes up, we have to stop. That means it's getting worse. Because at a certain point, when you keep fitting to the red curve, you'll be getting away from the green curve, which is what we use to check how biased our interpretation of the data set is. What else? Okay, so the final values are printed here. I'm not sure why this value is different from this value. That's very confusing, because they used to be the same. And the averages are quite far off from the best ones, which I don't quite understand either. Let me think about it. Let's see. So like the final test, that should be the same. Not sure why it's different. Let's see. It's right here. So, oh, Yeah, we're not supposed to find the best one. Okay. So when we write, instead of this, we should actually do p dot population dot get 0. Because basically, let me see. Well, we have to p dot compute error with train, and then p dot get best curve. Oh, that's, where is it? Find best curve. P dot population. Okay, so this program was incorrect. Let's just run it again. So what that did was it actually found the best curve that fit the validation set, which is called test. I know it's very confusing. Basically what it did was it found the one that best fit the green dots instead of the red dots, and then put out its error with the actual green set. And that's not what we want, because we want to calculate the best one that fits to the red set but has a good enough error with the green set. Yeah, so now they're the same, which is what it's supposed to be. Okay, now to get into the blue stuff. So the blue dots are the validation set, which is actually supposed to be the testing set. And what that does is, after the training ends, we're going to calculate the fitness of the curve on this fresh set to determine whether our training was successful or not. And I must say, usually the validation score is somewhere around 84.0 to 85. So this is quite a nice fit, because it's actually 83.69 here with the one that you haven't seen before, or the one that the model has not seen before. And I'm saying model because this is basically a machine learning model, except it's not like a neural network or anything else like that. It's like a genetic type of thing, a genetic algorithm to be specific, or use the right terminology. So yeah, I think this is quite interesting. And if you look up an online plot of early stopping or something like that, usually they have it continue on, like the red plot and the green dot, or the green plot. So like the green plot will start to bend up, while the red dot, or the red plot, oh my goodness, okay, the red plot will like smooth out, because it reaches a point where you can't really get any higher. But as you do that, the green fitness starts to actually get worse, because you're getting too close to red and straying away from the general sense of the whole data set. Also, you might be wondering, why is the training fitness worse than the test fitness if it's never seen the test set before? Well, the answer to that is the test set is a size of 100 dots, while the training set is a size of 300 dots. So when you have different sample sizes, it kind of messes with the actual accuracy, or the actual magnitude of the RMSE function. So that's something to note, because this is actually quite a large disparity. When like the training set is 3 times larger than the validation set. However, what's important is the curve, and as long as this works out, there's really no problem with the different magnitudes. So then down here in the bottom right, we have the average training and the average testing fitnesses. So you can see that the average is much worse than the best. And that's obviously because, like in any population, the average statistic will be a lot lower than the top statistic. Like for example, the average use of a word is probably something like 1.5. Like you're not going to use a word more than 1.5 times most of the time for all words. Like in an essay or across a collection of essays. But the top word will always be the, and I know that because, everyone says the most. And it's just like a key component of the English language. So the will appear way more times than any other word because it's number one, and usually in a population, number one means it either like has some feature that makes it higher than the other ones in some type of way by a lot. So that's just something to note. This is called the law of zip f. So there's a PSOS video about that. You can watch it. Yeah. Also, like, for example, in terms of income, like the top income earners have way more than the average by a large margin. So definitely you can expect that the fitnesses will be different between the average and the best. So yeah, that's about it for this video. Oh, maybe I want to go over the code. So did I learn anything new that like wasn't expected of me to learn? I learned how to use a sorting function, a custom one, in Java. So you have to like override the compare to function, which returns an integer. And basically, you can use your own custom comparator. And basically what I did was I used the .rmse of a curve to sort them into order of greatest to least. And you have to implement or import java.util, the sorting function. Let me see where that is. I actually use it here, I think. Find best curve. So if you want to find the best curve, obviously you have to sort the fitnesses or all of the curves by their fitness value, which I called RMSE. So I did collections.sort, which is a Java library, collections, and inside it there's .sort. So .sort the population, and then the best curve will then become population.get 0. And actually a big mistake I made was not having a way to calculate the best curve in different error or with different tables or data sets. Like every time I want to refer to the best curve inside of the or with respect to the red dots, I have to do population.get 0 after I sort by the or calculate the error by the training set, and then by the validation, which I called the testing set, big mistake, by the validation set. And then after that, I can then make the best curve equal to the population.get 0. Or actually I just did I had to make the population remain the same order that is sorted by the training data, if you understand what I mean. And then I can recompute the error into the testing, or no, the validation set, and only then can I use population.getZero to actually get the error or the fitness of the best red curve, so to say, on the green dots. So that's very annoying. You can see it right here. So first I had to compute error with train, find the best curve, and sort it at the same time. Then I had to, do all the stuff with making a mating pool and setting the best curve. But then when I want to actually get the previous best curve's error with respect to the green dots, I have to compute the new error with the testing set and then not sort it, but instead just do the first one in the population, which is the original best one, and take its fitness. After that, I just breed. And yeah, that's about it. So, thank you guys for watching this video. Let me see what else. The colors, yeah, I figured out how to graph all the different tables in different colors just using a for loop. And what I did was, I had 3 different colors, I had 3 different sets, and the sets are right here. And then I add them to this array list of sets called sets. Or it's actually an array list of tables called sets. I just called it sets to make it simpler. After that, I loop through from 0 to 3, and then I load in the individual sets to this t variable, and then I can plot all of them in different colors depending on depending on the I value. So that was quite clever, I think. But I mean, it wasn't that clever because I figured this out after I wrote this 3 times. So I kind of was pretty sad that I didn't figure this configuration out from the beginning. So that's bad planning. Don't do what I did. Also, plotting things was very difficult. I had to first scale 1 and then -1. So that basically flips the y value. But then when you flip it, you have to translate it up, if that makes any sense. Or is that down? I don't even know anymore. Wait, if you flip it up, oh, you have to translate by negative height, which goes down technically. Yeah. Because then, like, the world is reversed. So, if you translate down by height, that then moves like the flipped thing, the flipped canvas. So, this is kind of tough to explain, but let's say you had a canvas up here, and the canvas is, the bottom is right there. Or no, the canvas is down here below this line of slashes. And then when you do, what is it? Scale 1, -1. 1 means the y-axis, and then -1 means you flip it upside down. So you'd like flip this to up there, and then you'd have a canvas up here outside of your view. And then you have to translate by something, but you can't translate by height. Height no longer goes that way. It doesn't go down anymore. Height goes up, because that's what I want for plotting. So you have to translate by negative height, moving the whole thing down here to the normal place again. And then basically that just makes everything more convenient. So yeah, you don't have to do like setting the y value equal to height minus whatever you have. You can just do y value equals the actual positive version of it. So that was something I had to learn. But then with the graphing of the error history, or let's just say training history, at first I had two plots, like the training plot was above and then the validation plot was below. But then I realized I might as well put them into one, because that lets you compare them more obviously. So yeah, that's what I did. Originally I had different dimensions, or I thought I might need different dimensions, but then I realized it doesn't make any sense. So I just made it kind of customizable in case I wanted to move it anywhere else. I just decided to make these new variables. And I actually utilized p vectors for the location, because you know, .x and .y, that's very convenient, and you know what everything is named. You don't have to do like origin x, origin y. You can just do origin is a new p vector with two values in it, and it makes everything better. So that was very nice. I had a little bit of trouble with plotting the curves, but you know, I had it set in my mind. I wanted like a curve to go from the left side to the right side and all the points in between. And I figured out, oh, I can iterate from 0 to the actual generation count, and then divide the actual dimensions of the plot by, or the x, or the width of the plot by the current generation, or the total generation count at the time, and then multiply that by I to get the x value of the current point. So that was quite clever, I would say. Yeah, and here in mouse pressed, I decided, you know, during the testing phases, I don't want to wait the whole time for the whole thing to go through. I just want to click it and then make it work. But then later on, I realized, oh, it's a lot faster because I optimized some stuff. And then I didn't really need this anymore. So actually, let's just delete it. Yeah. Alright, so yeah, that's about it for this video. Thank you guys for watching, and see you guys next time.